Hello guys, good evening to you all, and I'm again here with my third session, and this session will cover the topic wave optics. Alright, so before we start this session, I would like to have a quick chit chat with you guys. I'm new to YouTube and this is my third session only, and I saw the responses to my first two sessions, and there were mixed responses. Some students liked my video, some students didn't like my video, some students didn't like me, some students liked me, and those kinds of things, So I'm very overwhelmed with the response that I'm getting now, and I believe most of you are happy, satisfied with what I have delivered to you. And keeping that in mind, I have brought you some new questions. There were a few suggestions and I have tried to deal with them. I've tried to incorporate them into this video. For example, one of the suggestions was to always speak in English, so I'm trying to do that. But I'm more fluent in Hindi, so at times I may just switch over to Hindi, but I'll make sure that I'm speaking primarily in English only. One of the comments was to speak slowly, so even that I will try today. I hope you are able, my voice is clear and you are able to understand what I'm saying. One of the comments was to include theory, a brief summary of theory of the chapter. So I've done that today. We'll quickly cover the theory of wave optics in 5 to 10 minutes or even less than that. So these were the things. Some of you wanted me to cover questions of previous year JEE papers. So I've picked some questions from that. But the thing is that my aim was to cover questions that could reveal the concepts, the hidden concepts or the concepts that have been taught to you, but they are not so common, so they keep on getting out of our mind. So my aim is to just have a brush up of those concepts, so that if they do come in exam, then you are ready to deal with them and they might just give you the edge. So with that thought, let's get started. So let's have a quick summary of the topic. We are dealing with wave optics, and in wave optics the primary theory that we use is of interference that we actually learned in the 11th class in the waves chapter. So here is a brief summary. Let me just go through it once. If x1 and x2 are the path of the particular point that we are discussing from two sources, we generally face a situation where there are two sources. Waves from the two sources reach a common point and then they superpose there. So two conditions are required for interference to take place. One is that the sources should have the same frequency, and the other is that they have constant initial phase difference. And if these two conditions are satisfied, then we call that the sources are coherent. So until the sources are coherent, we cannot have interference. So I'm assuming here that we are dealing with coherent sources. Having said that, let's say one of the sources is placed at a distance x1 from the particular point that is under consideration. The other source is placed at a point x2 from the point P, which is under consideration. Then x1 minus x2 will be called as the path difference. Alright. And we have taken mod because we are not sure which one is going to be greater. So if the mod of x1 minus x2 is n times lambda, then we say that constructive interference is taking place. And in constructive interference, the amplitude that we obtain at point P is A1 plus A2. This is also the maximum amplitude that we could have obtained using these two waves. Alright, now the second case comes when the path difference is not n times, it's not an integer multiple of lambda, rather it's an integer plus 0.5 times of lambda. In this case, the crest of one wave totally matches with the trough of the other waves, or the maximum displacement on one side totally gets overlapped with the opposite displacement of the other wave. So in this scenario, what happens, we say that destructive interference has taken place, and in this case the resultant amplitude at point P will be A1 minus A2, and we will take the mod because we are not sure whether A1 is greater or whether A2 is larger. So we have taken the mod. In this case, whatever intensity we get at point P is the lowest intensity, and in constructive interference, whatever intensity we get at point P is the maximum intensity that we could have obtained using those two waves. Alright, so these are not the only two possibilities. Other cases also exist, like the path difference may not be equal to n times of lambda, or it may also not be equal to n plus 0.5 times of lambda. In all other cases, the amplitude will lie somewhere between these two values. This is the maximum value that we can obtain, this is the minimum value that we can obtain, and in all the other cases the amplitude will lie somewhere between these two values. Exactly how much will it be, that can be obtained by this expression. Alright, so this expression is root of a1 square plus a2 square plus 2a1 a2 cos of phi 2 minus phi 1. Now what's phi 2 minus phi 1? It hasn't appeared yet. So phi 2 minus phi 1 is the phase difference. If the path difference is known to us, then we can utilize this path difference to get the phase difference also. How do we do that? That's a very simple formula and a very important one too. What we do, we multiply k. K is the angular wave number, or 2 pi by lambda. That's k, 2 pi by lambda. So we multiply k with path difference, and the result that we get is called the phase difference. So phase difference will be used in this expression. This expression is very similar to what we use or what we see when we add two vectors. So that will help you to remember the result. So AP, or the amplitude at P, will be given by this expression when these two cases are not applicable. This formula will still be applicable even if the case is one from among these two. Alright, so this is a general formula which deals with all the cases. Alright, so this is about it. Let's move on to the next slide. So IP represents the resultant intensity at P, that will be related to the intensity of the incoming waves as I1 plus I2 plus 2 root I1 I2, then cost the phase difference. I1 is the intensity due to first wave, I2 is the intensity due to the second wave, and then we have these expressions. So in case of constructive interference, this value becomes plus 1, so maximum intensity we get is root I1 plus I2 square. Alright, in case of destructive interference, this value will become minus 1, and if this becomes minus 1, then the intensity that we get is root I1 minus root I2 square. So this. Alright, so I minimum, this is the destructive interference. For general case, we are going to use this. Sometimes contrast ratio or distinction ratio word may be used in the question. So you should be aware of this, that these two words mean I max by I min. The maximum intensity divided by the minimum intensity is called the contrast ratio or the distinction ratio. Alright, so this is about the theory of waves that we are going to use in a particular case. That is the case of light waves. Alright, so this was related to waves. It is a general phenomena pertaining to waves. Now let's come to the YDSE setup. Alright, in 12th, the most important experiment as far as wave optics chapter is concerned is the Young's double slit experiment. So let's just have a look at the setup. I'm sure you're quite familiar with it. Just for the sake of completion, let's go through it. So we have a sheet with two slits in them. The slits are named as S1 and S2. D is the separation between them. Alright, and what we have done, we have kept a point source at a very far off distance from this opaque sheet. So what's the purpose of keeping point source at a very far off distance? Because when light comes from a point source from very far, by the time it reaches this opaque sheet, it will start behaving as a parallel beam. Alright, so what we want, please excuse me for this. Yes, what we want a parallel beam to be coming, and the parallel beam will hit this S1 and S2 slits at the same time. So what happens? The light that moves through this slit S1, it doesn't move straight as it would have moved when light comes through a window. So that will not happen, since the slit size is comparable to the wavelength of the light used. That's a mandatory condition for getting this experiment. So the slit size should be comparable to the wavelength of the light that we are using. If that happens, what will happen? The light that is coming will not move in like this only as it moves through a window. What will happen? The light will spread on the entire screen. The light from S1 will spread on the entire screen. Similarly, the same thing will happen for light coming from S2 also. So it basically means that any point P on screen now is getting light from both, because light moving through slit S1 has spread on the entire screen. Light moving through S2 has also spread on the entire screen. So any point of screen is now receiving light from both the sources. Alright, so what we do, we use geometrical results to figure out that what will be the difference of these two lengths, the S2P length and the S1P length. So difference of these two will become the path difference. Once we are aware of path difference, we are now in a position to figure out what kind of interference is going to take place. So to complete the mathematics, we use geometry such as this. As you can see, this S1 represents the first slit, S2 represents the second slit. P is a distant point. Why are we calling P as a distant point? Because another condition that you should be always aware of, this distance which has been represented here as L, but another common symbol or alphabet to represent this distance is capital D. In most of the textbooks that you may have read, that you have gone through, this would have been represented by alphabet D. Right now we are using L, we can use D also. So if this L is quite long, then it makes these two rays almost parallel to each other. Alright, if this L is quite long, these two will become almost parallel to each other. So we are going to get a situation like this. So if we drop a perpendicular from S1, then this length will become the path difference, because the other part of the path is common, is same. So this becomes the path difference, and on doing necessary calculations we get this value as d sine theta. See, what is theta? Theta is the angular position of point P. Now what is the angular position of point P? If we connect the midpoint of the two slits with P, then this angle is called theta. Okay, so this is the case. The part difference is d sine theta. If d sine theta becomes, this is the same that we have just now seen in the first slide. If part difference is integer times lambda, constructive interference takes place. If part difference is integer plus 0.5 times of lambda, destructive interference takes place. Alright. One thing that you may have studied in your coaching institutes or any other institution that you are going to learn things, you may have studied that since theta is small, we can write sine theta as tan theta also, and that ultimately it will become dx by d. What is x? X is the distance. I'll just show you what is x. Okay, I'll have to go to the previous slide. For this I'll have to rub this, so keep this in mind. I am just getting rid of this. Okay, so in this slide, this distance which we have represented by y, actually we also use x for this. So dx by d. If theta is quite small, then we can say sine theta is same as tan theta. Tan theta would be this distance divided by this distance. Alright, so we use that also. I'll again write the thing, you can just have a quick look at it. So d sine theta can also be written as d tan theta, which will become dx by d, or going by the figure that I have put up here, dy by L. Alright, so now this is actually something very critical, very important. I would just like to highlight this because I have seen many students keep forgetting this thing and they commit mistakes, right? What kind of mistakes? See, the original expression for part difference is d sine theta. This is the original expression, and it becomes equal to dx by d only when we are dealing with small theta. If theta is not small, then we should not be using dx by d. We should be using d sine theta. There will be questions in which you will have to take a decision whether you can consider theta as a small or not, and based on that you will have to decide whether to choose this one or to choose this one. The answers will be different. In cases where theta is large, the answers that you get by using this will be different from the answers that you get by using this. So you'll have to be careful. Alright, now just let's see some questions. We have spent enough time on theory now. I believe that will do the job. Let's quickly go to the questions now. So here is the question. Okay, the question says, in a Young's double slit experiment, the slits are placed some distance apart. I have just bent down a bit so that you can read the question. In a Young's double slit experiment, the slits are placed this much distance apart. Light of wavelength this much is incident. The total number of bright fringes that are observed in the angular range. I want students who want to attempt this question to have a go at it. Just attempt this question. I'm waiting for you guys so that you could solve this question and get to an answer. Okay, you can start solving the question and then you can see whether you are going in the right direction or not once I start solving the question. So let's get started, guys. Alright, we want to cover as much questions as we can. The session is very short. Okay, so let me get down to business now. So the question says, what I understand, we have been given the value of small d, that is the separation between the slits. We have been given the wavelength also. Alright, fine. Total number of bright fringes that are observed. So the situation is somewhat like this. These are two slits, d is given to us. This is the separation, and we have been given a range, like this is 30 degree, this is 30 degree. So they are saying minus 30 to plus 30. So minus 30 to plus 30, 30 degree on one side and 30 degree on another side. So in this particular range, whatever maximas are there, we had to tell the number of those maxima. Alright, we have to tell the number of these maxima. Alright, I'm doing a solution here. You have to tell me whether it's correct or not before we see the answer. I'm giving you an approach. Okay, you have to tell me whether the approach is, or rather you have to just tell yourself whether you believe that approach is right or not. okay, because by what you comment on my approach, it will be decided whether you know the theory or not. Okay, so let's just check this out. So one of the ways that I could attack this problem is this. Just have a look. So this angle is let's say 30 degree, and I'm not aware of this distance. Okay, the total number of bright fringes has been asked. Okay, so what I could do, actually the theory that I was thinking was it required the knowledge of D. So let me get to the correct solution only. What we can do is we can figure out the part difference here. We should write the part difference here. The part difference here would be D sine 30. Note that I'm using D sine 30. I'm not using dx by D. Or I could have assumed this as x and I could have started like that, but that would be a disaster because 30 degree is like a good angle. It's not a very small angle. So I'm going for d sine theta. So d sine theta is the part difference here. Alright. Okay. Now we have to find the total number of bright fringes that are present in this region. So what we are going to do, we are going to divide this path difference by lambda. Alright. So the ratio, can you tell me the dimensions of this ratio? What units will be there? This is part difference, which will have dimensions of length. This is lambda, it will also have dimensions of length. So this will be a dimensionless ratio. We call this as Z value. This is a very useful number to have. Why? Let me just show you. So D is how much? D is 0.30 mm. Okay, so D is here. Then sine 30 degree will become 0.5. I hope I'm like you can see this, divided by wavelength. Wavelength is 500 nanometer, so we can write 500 into 10 raised to power minus 9. Let's get rid of this millimeter by putting a 10 raised to power minus 3 also. So on doing the calculation, let me just do the calculation now. So what I'm doing, we'll get 10 raised to power 6 out of the 6, 3 is gone. Okay, 2. So I've got rid of all the zeros. Now the number remains is the number that remains is 320 divided by 5 into 5. So this 5 also gets cancelled. So it's ultimately 320 only. 320 is what is left. Alright, so what does that number represents? Okay, this number represents that delta by lambda is 320. So this number tells us that delta is 320 times of lambda. The part difference here is 320 times of lambda. What does this mean? Let's have a look. Part difference here would have been 0. Then as we go up, the part difference would increase. It will become, let's say, 1 lambda at some point of time. So we'll get a maxima there. Going further, it will become 2 lambda. Alright, minimas are in between, like 0 to 0.5 lambda, then 0.5 to 1 lambda, then 1 to 1.5 lambda, then 2 lambda. So as we are going up, the part difference is going on increasing, and each time the part difference becomes an integer multiple of lambda, we encounter a maxima. So what I can understand from here is, as we go up, the part difference will become 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda, and so on until it becomes 320 lambda. So 320 maximas are going to be present here. So 320 maximas here. The same thing will happen below this central line. So 320 maximas here. So total of 640. Is 640 the answer? Well, I can see 640 in the options. But be careful, guys. 320 above the central maxima, 320 below the central maxima, and there is one at central maxima, the 0th order maxima, which we call. So a total of 641 maxima should be there. Alright, let's have a check. So what was so special about this question? Was there something at all? Yes. The first thing, many of the students will falter in using dx by d as expression for part difference. So the moment they use, they are going to get the wrong answer. Firstly, the second trick in this question was to keep in mind that we have to count the central maxima also. Having said that, let's check the answer. Yes, it's B. All right. So let's move on to the next question. Again, next question is a tricky one. It's actually a tricky one. Let's just read this question. Consider a Young's double slit experiment as shown in the figure. What should be the slit separation D in terms of wavelength lambda such that the first minima occurs directly in front of slit S1? Let's just have a look at what the question wants us to do. Okay, so what I can understand from this figure is, first of all, it's not a regular YDSE setup. Why am I saying so? Because in YDSE setup, the separation between the slits and the screen is too large as compared to the separation between the slits. So in this example, situation is not like that. The separation between the slits is small d, and the separation between the slits and the screen is 2d. It's only 2 times of that. So this means that this is not a regular YDSE setup. So it also means that we should be careful while using expressions that we have derived for a YDSE setup. So this is one aspect of this problem. Let's see what the question wants us to do. Question says, what should be the slit separation d? So we want to find this separation, or we want to find the value of d, and the condition is that the first minima occurs directly in front of S1. So as we can see in this figure, the first minima is to be obtained at this point. The first minima is to be obtained at this point. This is separation d, this is 2d. Okay, so this is the case. Now again, let me present a solution. Alright, let me present a solution which students generally do. Okay, tell me if it's right or wrong. So the value of x for this point, the value of x represents the distance from the central point. The value of x is d by 2. So d by 2 is the value of x. Part difference is written as dx by capital D. Here capital D can be replaced by 2d. See this, if this expression is clear to you. What I have done, part difference, as you may have learned, is dx by capital D. So I have replaced d by 2 in place of x. I have replaced 2d in place of capital D, as is the situation shown here. And then this part difference, we want the first minima to appear here. The first minima will appear when the part difference becomes equals to 0.5 times of lambda. So if we solve this, what we are getting is d by 4 is equals to 0.5 lambda. So d should be equal to what? 2 times of lambda? No option like that. You know what? The person who has framed this question, or whoever the question whoever person made this question, he should have included an option like this also, and you would have found that more than 95% of the students are doing this question incorrect. But obviously this is not the solution, because we are not getting any of the options. We should do something different. But before we go into that, what's wrong with this solution? Well, the obvious thing is the expression that we are using, dx by d, it requires the angle to be small. Again, since this is d by 2, this is 2d, so the angle that is going to be formed is not small, so we cannot use these expressions. So what should we do at all? Well, the thing is, it's actually, if we are not preoccupied by thoughts of using what we already know, this question is an easy one. Let's just see how. We have to find path difference at point P. So one wave is coming from this point. So how much will this wave travel to reach P? I think this wave is going to travel a distance 2d. And how much the wave is going to travel if it has to come from S2? So to come from S2, it will have to travel this length. Can we calculate this length by using Pythagoras theorem? I think we can. So we are in a position to exactly write how much this length is. We can write this length also. The difference should be equal to 0.5 lambda. Let's do this actually. So S2P is d square plus 2d square root. Just have a check. D square plus 2d square, so root, minus S1P. S1P is 2d, and this should be equal to 0.5 lambda. That's it. We are done. You solve this, we get the answer. And I think you can solve this orally also. I did not move my pen to get the answer, or even you can just answer without moving a pen. So the answer should be what? I think it should be D. Let's have a check. Yep. So got this question. So we have done 2 questions now where the usual expression for part difference was not applicable. You have to be alert while you use the expression for part difference as dx by d. You should confirm that the point that you're dealing with is actually making a small angle, or its angular position is quite small, that you have to notice before you start using the expression. Let's see another question. Now this question says, in Young's double slit experiment, the part difference at a certain point on the screen between 2 interfering waves is 1/8 of wavelength. The ratio of intensity at this point to that at the center of bright fringe is close to. Now this question is actually an easy one, There's no trick involved in this question. It's quite a regular question. It just checks whether you are thorough with your topic or not, because if you are thorough with your topic, there's no chance that you are getting this one wrong. Let's see how. The question clearly states that the part difference is 1/8 of wavelength. So if we are already aware of the part difference, we can readily find the phase difference. Phase difference is 2 pi by lambda, that is k times of the path difference, which is this. So it becomes pi by 4. Alright, so we are aware of the phase difference now. If both the slits are producing the same intensity on the screen, then the resultant intensity will be I naught plus I naught. Here I naught is the intensity due to one slit, plus 2 times of root I naught into I naught. I hope you recognize this expression. You should be aware of it. This expression should be in your mind. If not, we have just seen this expression in the opening slide, or the first or the second slide, where I was revising the theory. So I1 plus I2 plus 2 root I1 I2. Then we had cos delta phi. Cos delta phi would be 1 by root 2, because cos pi by 4. So this is what we are getting. Alright, so if we do the calculations, we are going to get 2 I naught plus root 2 I naught. Have a check at this. This is what we are getting. Okay, so this is the intensity that we are going to get at point P. The question is asking for the ratio of the intensity at this point to the center of bright fringe. Now, what is the intensity at a bright fringe? To get the intensity at bright fringe, you can simply put a 1 here, or if you remember it by memory, the intensity at a bright fringe is 4 times the intensity due to one slit, if the slits are producing same intensity. So the intensity at a bright fringe would be 4 times of I naught. So we divide this number by 4, I naught gets cancelled, we are left with numbers only. We do the calculation, we'll get the answer. Okay, so what kind of answer am I expecting? 2 plus root 2 divided by 4, I naught will get cancelled. Root 2 can be written as 1.4. So 3.4 divided by 4 is 0.85 around. So I think C should be the correct answer, and yes, it is. Okay, so let's move on to the next question now. Again, in a Young's double slit experiment, slits are separated by some distance, which is given. The screen is placed 1 centimeters away. A beam of light consisting of 2 wavelengths. Alright, so this question is different from a regular YDSE setup, as it uses 2 wavelengths. Let's further read the question. Is used to obtain interference fringes on screen. The least distance from the common central maxima to the point. Okay, the question is a fairly straight one. If you have already dealt with the cases of 2 beams or beams containing 2 wavelengths, and if not, let me just explain what to do. The question is asking for a point where the maximas would coincide. So let's just have a look. Let's see what we are doing. We are in a YDSE setup and we are using a wavelength. Okay, let me just take an example. Let's say we are using a wavelength of 300 nanometer, let's say. Now one thing is that 300 nanometer is outside the visible range, but let's just forget right now. I'm trying to explain a point to guys who are not aware of this particular case, who have not seen these case, such a case. So give me 2 to 3 minutes. Just ignore the fact that this is outside the visible range. So let's say we have used a beam that contains this much wavelength, and in another case we are using a beam of 400 nanometer. Now the fringe width is given by capital D lambda by small d. So we can say that whatever fringe width we are going to get here, let's say if I write fringe width that I get here as 3 times of C, where C is, just a minute guys. So if we write the fringe width that we get here as 3 times of C, now what is C? C represents all the numbers like D, there will be common. The nanometer thing, that will be common. So 3 times of some number. Then beta 2 will also be represented by 4C. So do you agree with that? This is 300 nanometer, this is 400 nanometer. We substitute 300 here, we do some calculations. So if we take out the 3 and the rest of the numbers we calculate, we are representing that as C. The same thing we can do here also. So this is now 4C. So this is 3C, this is 4C. If let's say this is the screen for this setup, this is the screen for this setup. If I start figuring out where the maximas will lie, just have a look. Like one of the maxima will be here, the other maxima will be at a height of 3c, then the next maxima will again be at a height of 3c, then the next maxima will again be height of 3c, then again at a height of 3c. Okay, let's come to this one. If one of the maxima is like the central one is here, so the next would be at 4c, next would be at 4c, next would be at 4c, next would be at 4c. So this is the sequence. Now we want to check which of the other maxima, like the central, if these two wavelengths would have been used together in one setup, then this wavelength would have given us maximas in these locations. This wavelength would have given us maximas in these locations. So all cannot coincide. Certainly if the central one coincides, then the next one is at a height 3c, this is at a height 4c, they will not coincide. Then 6c, 8c, not coincide. 9c, 12c, not coincide. 12c was here also. So the 12c one, the maxima which is at a distance of 12c will coincide. So what can we make of it, this situation? We can make a rule now that in such cases we should look for the LCM of beta 1 and beta 2. LCM of beta 1 and beta 2, that is what we should look for. Okay, and if you think a bit, if you have not grasped the idea by now, think about it in a moment of peace and you will understand why we are taking the LCM. Okay, so now I'm leaving the calculation part. I think I've explained the question. You should be able to calculate the fringe width for 650 nanometer. You should be able to calculate the fringe width for 520 nanometer. And if you take the LCM of those two numbers, you'll get the answer. Okay, so I'm not doing the calculations now. I think I've explained it fairly clearly. So let's move on. So the answer will be this much. You can just do the calculations and you can check it. So let's move to the next question now. Now we have two coherent point sources, S1 and S2 are separated by a small distance as shown. The fringes obtained on the screen will be, I think we need to have a look at the diagram. So I'll just get aside and you can have a look. Now is this a regular YDSE setup? No, it's not. It's not a regular YDSE setup, because in YDSE setup the plane of the slits is parallel to the screen. Now we have a different situation, and what do we need to figure out in this particular case? We need to figure out the shape of the fringes. So again, not a very tricky one, but still let's have a look. So if we choose any point on screen and we join this to S2, let's say we have tied a thread here. Just imagine that we have used a thread and we have tied S2 with P. We have used another thread and we have, let me change the color. So we have used another thread and we have tied this point with S1 also. So the difference in the length of these two strings is going to tell us the path difference at P. Fair enough. I want to think about other points on the screen which will have the same path difference. Other points on screen which will have same path difference. Can you tell me where can I find those points? Just think about it. Whatever is the path difference or whatever is the difference of length of these two strings, I want to search for points where the path difference will still be same. Let me give you another hint if you haven't figured it out yet. Let's say we are keeping the strings like that. If we rotate the screen about an axis passing through this point, if we rotate the screen, then this circle or this particular joint will appear on all points of the circle. Like let's say we have put a small pencil here, somehow we are able to do that. Then when we rotate the screen, we'll find a circle there. And can I say that each point of that circle will have a path difference of what we have at this particular point, because we have not changed the lengths of the string, so the difference should also be the same. So what we can see from here, that if we are looking for points that give us the same path difference, then those points appear on circles. Now this actually means that the fringes will be circular in nature. Alright, like we will have a bright fringe, then a dark circle, then a bright circle, then a dark circle, then a bright circle in this particular case. So this is what is going to happen. Okay, so the answer would be concentric circles. Alright, I hope you are getting the hang of it. I hope you are clear with this. Let's move on. The answer has been shown. Okay, so now we have a question on polarization. Polarization is actually a very, very easy topic. If a question comes from polarization, you should attempt that question, because in all probability if you are if you have studied polarization, I'm not even saying that you should be an expert in it. If you have studied polarization, you should be able to answer questions pertaining to polarization. Let's have a look at this question. Beam of unpolarized light of intensity I naught is passed through a Polaroid A. Fine. So unpolarized light passed through a Polaroid, the intensity will become half. Okay, let's move ahead. And then through another Polaroid, okay, which is oriented to that, its principal plane makes an angle 45 degree related to that. I think it's a very straightforward question. Simple application of Malice's law. Okay, the Malice's law says that intensity will be I naught into cos square theta. So what is I naught here? I naught is the intensity of the beam after crossing the first polarizer or first Polaroid. Alright, and what is I? I is the intensity after the light or the beam has moved through the second Polaroid. So the first Polaroid always reduces the intensity to half for an unpolarized light. So I naught should be half of the initial intensity. So actually, as far as this question is concerned, here we should substitute I naught by 2, and for in place of theta, theta represents the angle between the pass axis of the two Polaroids that we have used. In this question, it has been given 45 degree, so that makes our job very easier. Cos square theta will be this, so the answer should be I naught by 4. Straightforward question, simple application of Malice's law. If such a question does comes in examination, then they are just trying to check whether you have covered the syllabus or not, because like you should be aware of Malice's law and you'll be able to answer this question. Okay, so we're getting the answer as C. Let's move ahead now. Alright, again a Young's double slit experiment. A Young's double slit experiment is carried out by using green, red and blue light, one color at a time. The fringe widths recorded are beta C or beta G, it is beta R and beta B. Alright, so green, red and blue, so that's what the subscript represents, and we have to decide the order of the fringe width. I think none of you can get this wrong. This is what I believe. Everyone, each and everyone who is watching this video or who has read this question should get this one right. I should not be even discussing this question. I want to move ahead. Can I, guys? I think, yes, I think you can answer this question. It's just you have to decide the order of the wavelength. So violet has the least wavelength, so it will have the least fringe width, and then the sequence is Vib, Gyor. So blue comes out of these three. After violet is not there, so blue, then Gyor. Gyor means the green, and then red. So red has the maximum wavelength, so D should be the answer. Red, green and blue, that should be the order. Yep. So worthless question actually. I took it just for the sake of completion. Okay, so let's move ahead now. Young's double slit experiment, intensity at a point is 1/4 of the maximum intensity, angular position of this point. Now that's interesting. Actually, that's interesting. That's not a regular thing that we do. In this case, what we have been given the intensity at a point, and then now we have to figure out the angular position of that point. So how do we start this question? We start this question by writing expression for resultant intensity, which is I1 plus I2 plus 2 root I1 I2 and cos delta phi. My aim is to figure out delta phi. So we substitute what? We substitute, the question says 1/4 of the maximum intensity. You should be careful here. It's not saying I naught by 4. No, it's not saying I naught by 4. It's saying 1/4 of maximum intensity. The maximum intensity is itself 4 times of I naught. So 4 times of I naught divided by 4. So we should write I naught here. So once we do that, equation becomes I naught equal to I naught plus 2 I naught cos delta phi. So on doing a little bit of math more, we are going to get cos delta phi as -half. Is this what I'm getting? Just tell me, guys. Yes. All right. So one part of the question was this. We have got the result. We have got the phase difference. Now we need to figure out the angular position. Okay. So keep this in mind because I'm going to rub this. So we are dealing with a point where the phase difference is cos phi is -half. So let's complete the question now. So once we say that cos delta phi is -half, okay, so what can we say regarding delta phi? Well, for those of you who said 120 degree or 2 pi by 3, that's not the complete solution. That's the correct, that's not incorrect, but that's not perfectly correct as well. What you should do, you should be careful in writing the general solutions here, because there will be many points on the screen where the intensity will be 1/4 times the maximum intensity. What all points have been given in question, we are not sure. It's not necessary that the point just above the central maxima where the intensity becomes 1/4 of maximum should be present here. It's not necessary. It can be present here, but it's not necessary. So we should be alert enough in keeping in mind that a point which is many points are possible, so we have to keep that in mind. So delta phi, what I will write the general solution. So cos delta phi is -half, so we are dealing with second and the third quadrant. So what I'm going to write, I'm going to write it as 2n pi plus minus pi by 3. Just have a look. The general solution of this equation, it can be written in other forms of also, but just have a look whether this one is correct or not. We are dealing with the third quadrant and the second quadrant, so I think this angle will end up in second and third quadrant. All right, so delta phi is 2 pi by lambda times the path difference. Path difference is dx by d. All right, we are assuming here that we are going to get a small angle. If not, then we'll have to change the solution. Let's just assume that the angular position will be small only, and after doing the calculations, if we figure out that it's not there, then we'll do something else. So 2n pi plus minus pi by 3 is what we are getting. So 2 pi can be removed, so this will become, I should make it, all right, so this is what we are getting. We need the angular position. Angular position means x by d. So x by d, in place of x by d, I will write theta. Theta is the angular position. So theta is n plus minus 1/6 into lambda by d. So this is the general formula that we have obtained. Yep. Okay. Now we need to see that out of these options, which can become equal to this. N should always be an integer. So you have two things to do. You can manage it in two ways. Either you can start checking, you should check whether lambda by d can be equal to this or not, and if it is equals to lambda by d, then n is coming out to be an integer or not. If n is not coming out to be an integer, then this option is incorrect. One of the way of doing is this. The other way is to keep on substituting values of n. You can try, actually this will not take much time. You can do the calculations quickly. You have to substitute values of n, integer values of n, like 0, 1, 2, 3, 4, 5. You can try 4 or 5 numbers, and in putting these values, if you get a number which matches with any of these, then that option is the answer. For example, if I try with, let's say, 0, then lambda by 6d, it's not there. Lambda by 6d is not there. Okay, this thing I think I should remove. Yes, I can move it. Yeah, it's better now. So if I put n as 0, it's not working. Let me put it as 1. So if I put it as 1, so 1 plus 1/6 will make 7. 1 will also not help. 1 minus, so this will be 5/6. If I put it 2, will it help at all? Just a minute. I think there has not been any calculation mistake. Okay guys, I faltered at a point. Please, this angle was not correct. Probably many of you already figured it out. It took me a bit of time to figure it out. Here should be a 2 also, 120 degrees. Second or third quadrant में बार बार बोल रहा हूँ. I'm speaking out loud second and third quadrant, but I faltered here. I took an acute angle, 60 degree I took. So a 2 should be here, and once we put that, the number that we will get here is 1/3. Now you can substitute n. Like if we put n equal to 0, so putting n equals to 0 give us the option. C option is the correct answer. All right. So yeah, my bad. Yes. Okay, let's move ahead now. Yellow light is used in a single slit diffraction experiment with a slit width of this much. If yellow light is replaced by X-rays, then okay, tell me which has got more energy, X-rays or yellow light? Or you can say X-rays have got more energy or visible light. I'm sure you're pretty confident, and that's correct also actually. X-rays have got more energy, which obviously means that X-rays have got less wavelength. All right, more energy, less wavelength. So X-rays have got less wavelength. So just read the question again. This is actually a trick question. So yellow light has been replaced by X-rays. Now that reduces the wavelength. Wavelength is reduced means the fringe width will also reduce. You might think so. Let's have a look at the options. Central maxima is narrower. Actually, this is a diffraction based question. It is not a Young's YDSE question. It's a diffraction based question. So in diffraction we have a central maxima, and the angular width of the central maxima is sine inverse of lambda by b, is something of this sort. So the thing is, if we decrease the wavelength, the central maxima becomes narrower. That's true. The statement is true. If we decrease the wavelength, the central maxima becomes narrower. But again, as I said, this is a trick question, guys. Many of the students can just tick option A, but what's the trick in it? Well, we have not decreased the wavelength slightly. We have decreased the wavelength significantly. Going from visible range to X-rays actually decreases the wavelength by quite a large factor, by 100 or even by 1000. So if the wavelength is so reduced, the opening of the diffraction slit, single slit diffraction we are discussing, that opening is no longer comparable to wavelength. Wavelength has become quite small. So we are now in the domain of geometrical optics. Whenever the wavelength is very small as compared to the size of obstacles or the size of apertures through which the light is passing, then diffraction effects, like, they are negligible, they are not noticeable, they do not happen at all. So when we have reduced the wavelength, we have very significantly reduced it. So that has rendered the whole experiment useless. We will not get any pattern at all. So the option would be D, no diffraction pattern. So this is a very important condition that you should always remember, that you should always check. Like, the examiner can always trick you on that in such a way. Okay, yep. Let's try another question now. Again, a question on polarization. I think two beams A and B of plane polarized light with mutually perpendicular planes of polarization. So we have two already polarized beam in these questions. Okay, we have not completed reading the question, but what I have read until now, we can see that we have two beams which are already polarized and their plane of polarization is perpendicular to each other. Okay, let's move ahead. So from the position where the beam A has maximum intensity, so beam A will have maximum intensity when the pass axis of a polarizer is parallel to the axis of A. So, and the beam has zero intensity. That's quite obvious actually, and once they have mentioned it, it helps us to gain confidence. Rotation of polaroid through 30 degree makes the two beam appear equally bright. Initial intensities are IA and IB, then the ratio. See, actually it's a very quite simple question. Once you get hold of the situation, like, there were two perpendicular direction. This was, let's say, the pass axis of A. This was, let's say, the pass axis of B. All right. So we kept the polarization initially in a position such that A beam was able to pass, B was not able to pass. Now we have rotated the polarizer by 30 degree. Like, if the light was coming like this, earlier A was able to pass completely. Now we have rotated it by 30 degree. So the intensity of A that will pass, again by Malice's law, it should be IA cos square 30. Now the point to understand here is that in the new position, in the new rotated position, the pass axis of the polarizer will make 60 degree with B, because B and A were perpendicular. So the intensity of B that is getting passed is IB into cos square 60. Okay, cos square 60. Rest you can do, I am very sure. So let's move ahead, guys. Now comes a very tricky question. Actually, this question, I will not say that it's a question that should come in mains, but I wanted to take a question which is really difficult. So this is the last question actually. So I wanted to go with a really difficult one just for the students who are here to get the content. All right, so let's have a look at this question. It's a really good one. So the question says, in a double slit experiment, the separation between the slits is 1 millimeter fine. Light rays fall normally on the plane of the slits and the interference pattern is observed on a screen placed at a distance of 1 meter from the plane of the slits. So what I can see until now is that it's a regular YDSE setup, no changes as of now. Let's move ahead. The arrangement is shown in the figure. I'm sorry, I don't think we have the figure right here. I'm not able to see, so probably we have missed the figure. I'll help you on that. Let's read ahead. When one of the slits is covered by a transparent strip of thickness 4 mm, the central maxima is formed at a distance of 2 mm from the point O. Okay, fine. Okay, when the entire apparatus, the second statement will come to this later, or let's just be done with it. Let's just read it. So when the entire apparatus, one of the slits still remaining covered, is immersed in a liquid, the distance between the central maxima and the point O is reduced to, I'll just move a bit sideways so that you are able to read the question. Okay, so we have to find the refractive index of the material of the strip and the liquid. Okay, so let me explain the question to you. We are going to need some space, so let's move on to the next slide. Now the setup is like this. We have a regular YDSE setup. What we have done, we have placed a strip here, a piece of glass you can say, and the width was given, I suppose the width was given to us. Okay, so because of this, what will happen, because of this, the light coming from this slab will slow down a bit, and as a result it will reach at the central point a little later as compared to the light that is coming from this. As a result, this point will no longer have zero part difference. Rather, a part difference of 0 can be expected where light from this slit can reach at the same time as the light from this slit. Keep in mind that the light coming from this slit has slowed down a bit because it moved through a denser transparent medium. Okay, so what will happen, we will get the central maxima here. The question says that this shift was around 2 mm, I suppose. We'll have to go back and check the value. So actually it's a result that needs to be derived. For those who know this result, this slab is going to create a part difference of this much. Alright, so because of this slab, the part difference that will appear at center is this much. So when we move ahead, we actually neutralize this part difference. So we should equate it to dx1 by capital D. This is the question actually says that we let's have a look at the question again. I think here we are at loss. We will lose the figure once we go back. The arrangement shows the figure when all the slits covered by transparent strip of thickness 2 mm from the point O. So x was given to us, thickness was given to us, mu was required. So we can calculate mu by substituting in those equations. You will be able to get mu. Alright. The other thing was the liquid, the refractive index of the liquid. How to get that? Well, in that case, we are going to use this. We are running a little short on time. My friends are giving me signal to stop, so I'll just do it quickly now. In that case, if the surrounding medium is not air, if it's some other medium, what we do? We use refractive index of slab divided by refractive index of medium, surrounding medium, which in this case is liquid. So this will become the effect now, and this should be equal to d times of x2 by d. Now what is x2? x2 is 0.5 that was given in the question. You substitute the numbers, mu slab is already known, mu L will also be known. So this is how we solve this particular question. So I hope you enjoyed this session. I hope I was able to satiate your desire for having good questions, and keep liking, keep subscribing, and keep commenting. I'll respond to your comment as much as I could, and thank you for all your supportive comments, and thank you for all your critical comments also, because they really help me to improve as a teacher. Having said that, let me bid goodbye to you. Now the other topics will be covered by AP Sir and Shadab Sir. So this is goodbye from me for this sprint course. Best of luck guys, good luck. Let's just see what we have in store on the next slide. So we have a bonus question, and the bonus question is this. I'll just get down so that you can pause your screens later on and you can read this question. It is related to the last question that we have done. I'm leaving this unsolved. You have to post your answer in comments and I shall be replying to it. Alright, okay friends, have a good day. Thank you, all the best of your examination. Do good, enjoy.